All right, so the big thing we're going to discuss today is something called linear transformations. So we're going to get in our Wayback Machine. We're going to go all the way back to remedial algebra, because some of the verbiage and some of the concepts are exactly the same as what you did in baby algebra. But the way we're going to discuss them in this class is actually quite different. So I want you to think functions in algebra. And by the way, they gave us a brand new computer. It's awesome. Problem was it's not hooked up to that, so we could. So I'm going to turn this because I know it's probably in the way a little bit. I want you to think function in baby algebra. So y equals f of x. Now in baby algebra, if I said what is the set of all the inputs of a particular function, what is that called? The set of inputs. The domain. And the set of outputs in baby algebra, we call it the range. Now, that's sort of correct. It's some of that's correct. It's not actually correct exactly. What we're doing in baby algebra is we have two spaces. In this case, we have the real numbers, and our function is what's called a mapping. We are taking things from the first set of things, and we're producing things from the second set of things. In general, if I don't get specific about my function, we say the domain is the set of real numbers. Now, there can be a particular function that doesn't use all the real numbers. But whenever we're dealing with functions, we're only using real numbers. There's no complex numbers anywhere in here. We're using real numbers. So we're always starting with the concept, my input comes from here. I may use the whole set of real numbers, I may not use the whole set of real numbers. That could be specific to the function, like a natural law. Okay? Now, the second set of function is also, or the second set here, the output set is also the set of real numbers. Now, I don't necessarily use the entire set of real numbers, but that's where all my outputs come from. So this guy is called the domain. Does anyone know what this one's called? Some of you have heard this in maybe another class. In discrete means this one. The codomain. Yeah. The first set is called the domain. The second set is called the codomain. Now, a particular function, f of x equals x squared. How much of the codomain am I going to use in that one? I'm only going to use the non-negative numbers. I'm only going to use half of it. The portion of the codomain I use, let's say that's the portion I use. That's called the range. The range is not the same as the codomain. The range is a subspace of the codomain. It's the portion of the codomain that that particular function actually used. Before I start the problem, everything's eligible. Do you agree? Everything's eligible before I start. Now, if I was talking about, lines, not horizontal lines, just y equal mx plus b, well, then I'm using every real number and I'm outputting every real number. That's easy. If I'm using logarithms, I'm only using positive numbers, but I'm still outputting all real numbers. If I'm doing exponential functions, I'm using all real numbers, but I'm only outputting positive numbers. Every function is different, but every function draws upon these two sets. Does that make sense? That's why it's the domain and the codomain. That's the proper language we use, and that's what we did way back in baby algebra. Now we're going to be doing a little bit differently. We're going to be looking at, instead of going real number to real number, we're very specifically going to be going from Rn to Rm. We can go to other vector spaces, but what we're going to be doing, we're going to be purely using vectors. We can do other tangential things, but we'd spend a lot of time on stuff that we're really never going to use. A linear transformation is primarily designed for this. And so we use a slightly different symbol. Instead of f, we use t. T for transformation. So a transformation takes a vector from the first set, acts upon it like a function, and produces a vector from the second set. This is actually how you can change the dimension of a vector, is by the transformation. So I'm going to give you a really simple example. And here's the notation. T is going to map R3 into R2. This is how this is written. T maps R3 to R2. The arrow tells me which way I'm going. So that means my input will be vectors in R3. My output will be vectors in R2. Okay? And T is defined as follows. Okay? I'm taking vectors in R2, I'm taking vectors in R3 and I'm outputting vectors in R2 based on this definition right here. Are we okay with that?
Is that just an example definition?
This is an example, yes.
Okay.
There's an infinite number. You can do anything you want. I know what he's thinking. So all problems will use this one. No. This is an example. So you notice I'm going to give you a vector in R3. Regardless of what x1, x2, x3 are, I'm telling you where they're going to end up. But notice that this vector is two-dimensional now. So I want you to find T of -1, 3, 6. What will this equal? So you got 5, and what was the other?
-27.
-27. Okay? This is called the image. Let's just call for, let's be lazy, vector V. This is called the image of V. You input the vector V, your output is called the image of V. Not really all that exciting, but that's, again, the language. Now, what if I said, what vector V, and by the way, this is, what I have right here is actually technically, you can write it like that. T of the vector, like I said, T of it, it's the same thing. What vector V solves T of V? Let's keep it really simple. What vector V solves this? Now I'm giving you the answer and I'm asking you for the input. So I'm asking you for, I'm going to put in parentheses, find the pre-image. If putting a vector into the input, my result is called the image, then I'm starting with the result and I'm asking you where it came from, then I'm asking you for the pre-image, the thing that came before. Again, it's just language. So the image would be the output, the pre-image would be the input. Okay? So I'm asking you for the pre-image of 7, 2. Well, how would I find that? What do you think?
Maybe we're going to use a matrix.
Well, let's set up a system of equations. My system of equations probably looks something like this. What do you think? Does that look about right? And as Matthew says, a matrix, by the way, are we recording? Just want to make sure. Yeah. I hate to say I love you, GoPro, but I don't have any faith in you anymore. So if I write this as a matrix, 1, 2, 0, 3, 0, -4, times x1, x2, x3 equals 7, 2. Oops. So this is what I'm asking you to solve. Therefore, what's the easiest way to do this problem? We know this from experience. Augment the matrix, yeah. I'm writing it this way because this is actually what we're solving. Ever since the beginning of class, we realized all system of equations can be written as matrix products. And a lot of times it's very practical to write it. But when I'm actually doing this one, yeah, I just want to augment that. So let's do that. Okay, so if I do -3 row 1s added to row 2, -3 of these added to this would be -19. That doesn't look very pretty. We can parameterize this any way we want, but it's going to be kind of icky. Don't you agree? You all agree it's going to be a little bit icky? But, by the way, is it consistent?
Yes.
Yes, it is. Definitely consistent. Okay? So, because of these guys, maybe let's let, how about x3 be, how about 3t? Then what would x2 be? Well, 3t be. Well, I'll write it out. Negative 6x2 minus 4 times 3t equals negative 19. Oops, sorry, not square root 2. Negative 6x2 equals 12t minus 19. So x2 equals negative 2t plus 19 over 6. Does that look right? I didn't mess that up. Does that look okay?
Yep.
Now what about x1? Back here. So x1 would equal 7 minus 2x2. So that would be 7 plus 4t minus 19 over 3. So that'd be 21 thirds minus 19 thirds, or 4t plus 2 thirds. Yikes. Kind of ugly, but that would work. Okay? You all with me so far? So, is the answer unique?
No.
No. And we should know that, and I'll explain why in a moment. We should know that. I'm going to do it over here. I have space. I don't want to erase any of the other stuff later. Assuming we've made no errors, and it's always a big assumption, it looks like anything in the form. I mean, read x1 to me, it's too far away.
4t plus 2 over 3. Negative 2t plus 19 over 6.
And then t. So any vector of this form. Yeah, do.
So
Not
when you're
3t.
parameterizing, I'm a little confused how you chose 3t.
Oh, 3, sorry. That should be 3t then, shouldn't it?
Oh,
Well, the idea being neither one of these is a 1. When one of them's a 1, you always pick the other one, but neither one of them's a 1. So really what I want to do is, you could say 4 of these and 6 of these, so I did more like 2 of these and 3 of these, so that, so I got an integer coefficient rather than a fractional coefficient. That's why I did it that way. Integer coefficients are always better because they're easier to work with. I have no control over that part. Right, that was going to be a fraction no matter how I parameterize it, but I avoided, do you notice that my t's don't have any fractions in front of them? There's an infinite number of correct parameterizations, but there aren't a whole lot of efficient ones. By the way, could I have gone 6t instead of 3t? Yeah, then the other one would have been 4t. I just saw that 6 and 4, 3 and 2, I was being a little bit lazier. Now, can we write this in a better form?
t 4 negative 2, 3.
Now, let's check something really quick. If I take this and I put it in here, 2 thirds plus 2 times 19 is 6, so 2 thirds plus 19 thirds, that's 21 thirds, or 7. 2 minus, so where are we? Oh, 2 minus 4 times 0, that's 2. That gave us 7, 2. Well, there's our unique solution. No. Now, add 4, negative 2, and 3 to each of these, and that would have also worked. What happens if I put these numbers in? 4, negative 2, 3. 4 plus 2 times negative 2, that's 0. 3 times 4 minus 4 times 3, that's also 0. Oh, that's interesting. Every multiple of that vector gave me the 0 vector as an output, didn't it? That's actually the most important thing, just so you know. Just saying. We'll talk about that one in a moment. So we found there's an infinite number of preimages, and we expressed it in the form xh plus xp. That should feel kind of familiar. We've done that before when we solved system of equations in general. So, an interesting concept. How did you know that it was going to be a parameterized problem as opposed to one answer?
3 inputs and 2 equations.
Yeah, that's one way of thinking about it.
You're losing a dimension.
I'm losing a dimension. Let me give you the simplest example of all. I'm going to take every point in 3 space, every point x, y, z, and I'm going to project it onto the xy plane. So x, y, z is going to go to xy. Not xy 0, xy. Do you agree? So every point xy, where did it come from? Well, it came from xy1, xy2, xy3, xy4. In fact, everything on a vertical line. There are infinitely many points that could have produced that point. Therefore, when I work backwards, there's an infinite number of possibilities. Whenever you go bigger to smaller, that's called a projection. You're going to be able to get a nice, happy answer. It's when you go backwards that you would have to parameterize. Because, again, think of, 3-space projecting onto the xy plane. That's the easiest way to think about it. Okay? Here we go. So, one way to describe a linear transformation is this. Now, what makes something a linear transformation? It has 2 rules. Okay? So, I'm going to map, just in general, T is going to map, again, Rn into Rm. Yeah, those will be the same often. They don't have to be the same. In fact, the most common problems that we will eventually do will probably be R3 into R3. We can handle it. R2 into R2 is a little too narrow, too specific. R3 into R3 and R10 into R10 is going to look the same, just less algebra. So I have this situation right here. Okay, so if I took V and W in Rn, there are 2 things that make something a linear transformation. Here's what, again, these are the 2 rules, the only 2 rules you have to follow. And that is that T of V plus W equals T of V plus T of W. The transformation of the sum is the sum of the transformations. And the second one is scalar multiple of V is scalar multiple of the linear transformation. That should sound really familiar from a calculus standpoint. What behaves that way in calculus? The thing of the sum is the sum of the things, and the thing of the scalar multiple is the scalar multiple of the things. Limits, derivatives, integrals. Oh, yeah, they'll have that property, don't they? Now, with limits, the limit of a sum is the sum of the limits. The limit of a scalar multiple is the scalar multiple of the limits. Those are essential for proving all the calculus properties of derivatives and so on. But limits had other properties, like the limit of a product is the product of the limits. Is the derivative of a product the product of derivatives? Is the integral of a product the product of the integrals? No. Sums and scalar multiples were the only things that extended, but it turns out they extend into many, many other areas in mathematics. And so it turns out for linear transformation, those are the 2 key things. So when I'm defining a transformation, we can actually prove it's a transformation by proving this generically by just taking 2 random vectors, and we can go through the process. I'm not going to do that for this stuff, but there are proofs that we're going to do that involve this. So one of the ones we often put together that make it really important, and this is, again, it's kind of a big thing if I put this into one statement. If I said, I want C1 of V plus C2 of W. The linear transformation of the linear combination is the linear combination of the linear transformation. So if I pull it apart as sums first and then I pull the scalar multiples out, we can see that's true. Now, doesn't everything in math work this way? No? Oh, wait a minute. So you're telling me if I take the cosine of x1 plus x2, that's not equal to the cosine of x1 plus the cosine of x2? So if I said e to the kx, that's not equal to k e to the x. All right, how about if I took C1 x1 plus C2 x2 and I cube it, isn't that C1 x1 cubed plus C2 x2 cubed? Isn't that always true with, don't all functions work this way?
I wish.
Or does it kind of, yeah. In algebra, by the way, if you're in a baby algebra class, they do. Right? The square of the sum is the sum of the squares. Everybody knows that. The cosine of the sum is the sum of the cosines. Or is it more the case that that basically never works? So, wait a minute. So in function world, is this ever true? Huh. True?
Yeah.
Just using that definition. It seemed to work, didn't it? How about the next one? It seemed to work. What was my original function? It's a line, which is linear. So only lines have this property, no? No? Careful. What if I do that? Won't work. Because I'll have a plus b, but not in both cases. I'll have a plus b, but... So it's not just linear, but linear through the origin. So in every dimension, any linear equation in any dimension you're in that passes through the origin. So in 3D, I have a plane that passes through the origin. It's going to be a linear transformation. In every dimension, a linear equation that passes through the origin will actually work as a linear transformation. That's it. That's why it's called a linear transformation, by the way. I can't have exponents or functions. Now, I can't have square roots or cosines or e to the x's. I can only have linear equations, and they have to pass through the origin. That's actually one of the hugest ones of all. So, if I input the zero vector from my first vector space, I have to output the zero vector from the second vector space, period. Not the number zero. We're never going to get the number zero as an output because you're dealing with vectors as inputs and outputs. Wow, that's kind of restricted, isn't it? I mean, this is all of a sudden really, really specific. Okay. Let me keep going. Now, I've given you an example of how to write a linear transformation by giving you the input and then giving you the output in vector form. But that's actually not the most common or practical way of doing it.
So would a vector value function be considered a linear transformation since you're going from scalar to vector?
Well, your inputs are purely vectors.
Because can't scalars be represented as vectors in R1?
Yes, but if they're not, again, lines through the origin, ultimately. Yeah, so you know, you're wanting to stick functions in there, but if they're not linear functions through the origin, it's not going to work. Yeah, it turns out it's very restrictive, but there's a whole lot of things we can do with that. Now, I'm going to give you an alternate definition of a linear transformation. I'm defining the linear transformation from R3 to R4 as a product of this matrix times my input vector. So how does that work? Well, what would T of x1, x2, x3 look like then? It's got to be a vector, by the way. Well, the easiest way for me to do that is just to, how about if I go like this? do you think? Will that do it? Turns out the matrix multiplication representation is, these are saying the exact same thing, but usually that's easier to work with, less writing. Easier to keep track of. Now I want you to tell me something about the shape of the matrix. This is really important. What is the shape of the matrix? 4 by 3. But I went from R3 to R4 and the matrix was 4 by 3. You think that's some kind of rule? Yes. Because this was 4 by 3, and what did I multiply it by? 3 by 1, and what was my result? Oh. So, going back to here. By the way, I'll just make it really simple. Every linear transformation that exists, I looked at all of them last night just to make sure. Every one that exists can be written as a matrix product. There's no exception. Even if you're going polynomial to polynomial, you're going matrix, whatever you're doing, still a matrix product. What would the shape of the matrix be? M by n, for the exact same reason, because I have to have these vectors in Rn have to be multiplied by that n to make it match. Oh, so that's a huge one. Is that one we could easily get backwards? Yeah, I mean obviously there are mistakes that could be made. We'd rather not make them. So a linear transformation written as a matrix product is way more practical. All right, now my first example, I said let's do t from R3 to R2, and I said t is going to take vectors in R3 and write them as vectors in R2 as x1 plus 2x2 and 3x1 minus 4x3. Okay, that's what we started with. Then I gave you a specific example and I said solve it, and you set up a system of equations and you solved it. Let's suppose I didn't give you the specific 7, 2, I just said in general. When you perform this, what are you going to get? You're going to get that. Now, I'm not supposed to tell you this because this doesn't come up until section 6.3, which is a week from today. No, a week from Wednesday. But I'm going to tell you now because it's kind of an oh duh. If I give you the linear transformation in vector form, you can tell me the matrix was doing 0 work whatsoever, even though there's a whole bunch of theory that has to take place before I can actually show you that. And if I give you the matrix, you can tell me what that is without doing any work whatsoever. Do you notice anything here? Yeah, it's that easy. 100% of the time, you can just read the coefficients and write the matrix down. It's actually always that easy, and I wanted it to be that easy on day 1, even though from a theory standpoint, there's a whole bunch of stuff we're supposed to learn first. You're supposed to start with the standard basis, run it through there, write your outcomes as combinations. It's pretty much an oh duh. Once you do 2 or 3 problems, you go, you know, I noticed that the matrix looks just like the order of the things in the vector. Yeah, well, yeah, it kind of has to. Otherwise, nothing would work. So when I did this out, here's my result. What if I started with this? You all agree that when I multiply, this is what I'm going to get. What if I'd started with this? Can't I work backwards to give you the matrix? Look at the coefficients. Look at how many terms. That's the key. These aren't showing up as columns. They're showing up as rows. Okay? Interesting. And by the way, that's extremely useful. Where we're going with this is eventually we're going to figure out there are certain vectors, if I input them, will give me output that is really nice and really friendly and really useful and so on. That's kind of the point of this chapter, is to figure out, once I understand the concept of this, excuse me, then what vectors can I input to get the results that I need, and so on. And then that's the segue into the next chapter. But now we're just really learning the rules and the vocab. So now, let's go back to this problem here. If I had asked you to solve this question here, we just did this a few minutes ago and we got an answer. It was our XH. I didn't call it XH, I said it was XH. What was it? It was t times what vector?
4, -2, 3.
4, -2, 3. You're saving me time of redoing the problem. So every multiple of this vector. If I go back to here and I go 4, negative 2, 3, that gives me 0. 4, negative 2, 3 gives me 0. Doesn't this represent every solution to this? This is the homogeneous equation. If I said, what gives me every solution to the homogeneous equation, what is that called?
The null space.
That's called the null space. So this would be a basis of the null space, wouldn't it? The null space of that matrix. But the problem is, I didn't start this problem with the matrix. I said this, there was no matrix associated with this. We figured out what the appropriate matrix would be. We came up with the matrix, okay? There was no matrix in the question. So I really don't say the null space of the matrix that isn't there. It's the null space of the matrix that I'm going to figure out as the matrix that goes with the problem, then I'm going to do everything. But the question didn't have a matrix. The question was input a vector, output a vector. So we use slightly different language, okay? And it goes with the null space. But it's different verbiage that means the same thing, but it's a context thing. So I have a vector here, v. It gets taken to T of v, which we'll just call vector w. So vector v lives in the first vector space. Vector w lives in the second vector space. Now, it is a linear transformation. So I know if I do the linear transformation on the 0 vector that lives here, right? We know that's going to go to the 0 vector that lives here. Oops, sorry. We know this. Might there be other vectors that get sent to the 0 vector? Might there be another vector that gets sent? Well, over there, wasn't every multiple of that one? By the way, is 0, 0, 0 one of the vectors? Yeah, if t is 0, then 0, 0, 0 is a vector, but it's not the only vector. So is it possible there's a whole set of vectors? There's a whole set of vectors, including the 0 vector. See that vector there? Every multiple of that vector in this scenario would be going. There's infinitely many vectors that would all go to one vector. Now, in the matrix of the transformation, okay, if I define T of V as A times V, we now know what the null space of A is. That's considered the most important of all subspaces, the null space of that matrix. I know what it is, I know how to find it. But I didn't ask the question with a matrix. But aren't I asking for the same thing? If I create the matrix and I solve the problem, I get that. But there's no matrix in Rn. There are only vectors in Rn. So what do I call this set, which is equivalent to the null space of the matrix? This is called the kernel of T. Some of you have heard the term kernel before. This is what it refers to. The kernel, first of all, lives in the domain and is the set that gets mapped to the additive identity of the codomain. Now, I'm going to say additive identity, even though we're dealing with pure vectors right now, so it's obviously the 0 vector. This is really from any vector space to any vector space. So technically, and I'm going to show you a really cool example where you're going from polynomial to polynomial. So you wouldn't say vector in that sense, right? You'd say the number 0 in that case. But if I was going from a matrix set to another matrix set, I wouldn't say the 0 vector, I'd say the 0 matrix. So the additive identity, the set of everything in the domain that gets mapped to the additive identity of the codomain. That is called the kernel. If I have a matrix for the transformation, when it's vectors to vectors, there's always a matrix and it's always easy to find. The null space of the matrix is the kernel of the transformation. They're the same set. I use different languages because I'm talking about one, I'm directly talking about a matrix. One, I'm talking about a set of vectors. Now, I needed a matrix in order to discover it, but there was no matrix given in the problem. Is everybody okay with that? So they go hand in hand. Okay? Now, as I map one this way, I'm going to take points on the floor. The floor is the XY plane. The floor is a cartoon character. He lives in 2 dimensions. So X, comma, Y, and that's it on the floor. I want to take things from your TV screen and I want to project them out into the room and make them 3D. So I want to take the point XY and make it XY something. So if I take every point on the XY plane and I go this way, will I get all of 3D? No. What will I get?
A plane in 3D?
Yeah, I'll get a 2-dimensional subspace of 3D. I can't go from R2 to R3 and get all of R3. I can go from R3 to R2. Bigger to smaller is easy, right? We call that a projection. But I can't do it the other way. How many have ever worn 3D glasses to like watch a movie or something? I can't. It kind of messes with my brain. Do you actually see things in 3 dimensions? No. It's literally like this. If I close one eye, you all just became a picture. You're all 2-dimensional. There's no depth perception. What 3D glasses does, it makes each of you a cardboard cutout. That's still 2-dimensional. It's just Tim's cardboard cutout is now further away from me than Matthew's cardboard cutout. Do you understand? That's how it actually works. You didn't become 3-dimensional, but I can now see you in 3D, but you're still 2-dimensional. And it's kind of a weird concept. But everybody would be a cardboard cutout, but now I can see depth. That's what the 3D glasses do for you. So do they really make things 3D in the same way? No, but it's kind of a cool effect. I cannot get all 3 dimensions starting with 2. Because I can only take linear combinations of those guys. I can't get all 3D. I can get a 2-dimensional subspace of R3. So when I'm going the other way, am I necessarily going to use up all of Rm? No. When I went 3 to 2, I used up all of it. But when I go 2 to 3, I didn't necessarily use up all of it. I may have only used this much of it. What do we call the amount we used up?
Range.
The range of T. The range of T is the amount of the codomain that you use up. Now, there's 2 of the most important words. The kernel is non-empty. The kernel has to have at least the 0 vector here. What if the kernel consisted of only the 0 vector?
The range would be only 0 vector?
Maybe. Well, it depends on the original dimensions too. But what if the kernel consisted of only the 0 vector?
And it's definitely...
Actually, go to a previous example. When we did this problem, didn't we get an answer that was xh plus xp? So we said there's infinitely many solutions. But what if this was only the 0 vector? Then wouldn't xp be the only solution to the original equation? Meaning I got a unique solution. Ooh, think the equivalent conditions, all the stuff that goes up with that. If the only solution to the homogeneous equation is the trivial solution, in other words, then everything else gets unique solutions. Good things happen, in other words, good things happen. What if this was only the 0 vector? What if the 0 vector was the only thing? Here's what I want you to think of. If I give you any vector in this set and I asked you where it came from, you know you can solve that problem. But the answer may not be unique. It may be parameterized. And it would always be of the form xh plus xp. What if xh is the 0 vector? Then it means everything here came from a unique input. What do we call that in baby algebra? When everything from the output has a unique input. We say it is 1 to 1. That's one of the more important terms you ever learned in your math life. 1 to 1. 1 to 1. First of all, we have to start with a function. We don't talk about non-functions being 1 to 1. I have a function. But 1 to 1 means, function means everything in the input has a unique output. What does 1 to 1 mean? Every output had a unique input. So that means there's a 1 to 1 correspondence between every input and every output. Even if they're infinite, there's 1 to 1. This guy went to one guy, and this guy came from one guy. Think of a parabola. That's a function, but it's not 1 to 1 because every output had 2 potential inputs. Right? So what was the rule in baby algebra? How did you know graphically if something was 1 to 1? I just did this recently in the 116 that I'm teaching.
Horizontal line.
Yeah. So in other words, if I'm looking at a graph and it's always going uphill or it's always going downhill, never turns around like a parabola. So one way of saying horizontal line test, always uphill, always downhill means one direction. Mathematical term for one direction is monotonic.
Monotone.
Monotonic means one direction. Okay? Does everyone understand that? I think it's adjective versus noun at that point. Yeah. It's like isomorphism and isomorphic. One's a noun, one's an adjective, but they're from the same context. If it's always going uphill or always going downhill, we say it's monotonic. It has one direction. Then it will be one-to-one because it also passes a horizontal line test. But that only works in baby algebra when I can draw a two-dimensional picture. It's not going to work in n dimensions, is it? So the concept of one-to-one is it's an easier concept in that if the only solution to the trivial equation is the zero vector, in other words, if my kernel consists of only the zero vector, then that means every time I work backwards, my xh was the zero vector, meaning I did get a unique solution. So we say that t is 1-to-1 if and only if, and the notation we use is K-E-R of t. We're lazy. We never actually write the word kernel all the way out. It takes way too long. And technically we should write, it's the set. If the only thing in the kernel of t is the zero vector from the domain, then we say the t is 1-to-1. 1-to-1 is really, really important, by the way. Okay? 1-to-1 refers to what's happening in the domain going this way. Now, what if? We went from R3 to R2, and I can get any vector in R2. R3, when I shrink it down to R2, is going to basically produce all of R2. I'd have to come up with some weird example not to. So, what did we define the range to be? The portion of the codomain that we actually use. What if we use the whole codomain? What if the range is the entire domain? RNG of t the word, you may have heard this word before. Onto. How many have heard the word onto before in a mathematical context? Do you remember what the concept was?
It was for functions, I believe.
That's probably a good thing. So 1-to-1 has to do with the domain. Onto has to do with the codomain. If the range is the entire codomain, now let's go back to baby algebra. Just simple lines. M is not 0. Any simple line, I'm using the entire domain, I'm generating the entire codomain, and it's clearly a 1-to-1 function. Do you all agree with that? So the equation of a line would be 1-to-1 and onto. Okay? A logarithmic function. Think of a logarithm, right? What the graph of a log, the output is everything from negative infinity to infinity. So a logarithmic function is definitely onto. Is it 1-to-1?
No.
No, because I can't even use the 0. Yeah, that wouldn't work, would it? Ah, okay. Now, strangely enough, okay, how about a parabola? Is a parabola 1-to-1? You say, no, it's not on one because one output could come from two inputs. Is a parabola onto?
No.
No, well, I'm only using half of the real numbers. So if you think about baby algebra, you can take every function you could even imagine in baby algebra and you can tell me 1-to-1 onto. It's pretty easy. Why? Because you have a two-dimensional picture in front of you. That definitely makes it easy. So now we step back and say, I can't draw a picture, so now I have to look at the results. So my input are vectors from the first set, my output are vectors from the second set. Now, dimension is really, really important. And I'm going to do this. This is a proof that I'm going to do later, but I'm only going to suggest it now so it kind of works its way in your brain. Can you have a transformation be both 1-to-1 and onto at the same time? It certainly seems reasonable, doesn't it? In fact, that's probably a really good thing. You know, that'd be kind of like saying a set of vectors is both linearly independent and spans, now it can be a basis. That's really powerful. Can a transformation be both one-to-one and onto? Yes, it can. If it's one-to-one and onto, that means I can go back and forth. Now, this is something we're going to define later. But it means I can go back and forth. You give me any input, I'll give you the output. You give me any output, I can give you the input. Life is good. That's the magic key that allows you to go back and forth. That's how we go from a vector space of vectors to maybe one of polynomials to one of matrices. Has everything to do with it being one-to-one and onto. And there's only one way it can be one-to-one and onto. I'll say if t is one-to-one and onto, then there is one thing that must be true. It's not an if and only if. But there's one thing that must be true. The only way you can be both is if you're going from same dimension to same dimension. I always just say same to same. I'm going from R4 to R4. Now, I just gave you 100 tiles. The floor needs 100 tiles to cover it. We now know it's exactly the right number. Therefore, my tiles are either both linearly independent and they span, or it's neither. Because any overlap at all means it wouldn't span and also wouldn't be linearly independent. We know that when we have exactly the right number of elements, it's either both or it's neither. Everybody remember that? That's kind of huge. So if I give you 3 vectors in R3, if you show independence, they're going to have to span because the dimension is 3. There's exactly the right number. But if it's not independent, then it also can't span. If I'm going from same dimension to same dimension, then it has to be both, or it has to be neither. How could it be neither? Let's take the most boring example. I'm taking everything in I'm going R3 to R3. I have a very clever mapping. Everything R3 to R3. And here's my mapping. T is going to take every vector in R3 and it's going to send it to the recycle bin. I'm going to take every vector in R3 and send it to the origin. Is this one-to-one? No, because my range consists of one vector in R3. Is it onto? No. This is pretty boring. I went from R3 to R3, but it's neither one because everything, by the way, all of R3 would be the kernel, wouldn't it? All of R3 would be the kernel in that case if everything got sent to the 0 vector. This is boring. The only way you can be both is to go same to same, and then it's either both or neither. And the most common problems we're going to eventually work with is same to same, because that's where all the really important information lies. When I first started talking about the 4 fundamental subspaces, I used a non-square matrix so you could see the differences between like the 2 different row spaces, right? The row space of A versus the row space of A transpose, null space of A. Then eventually I said the rule of thumb is going to be that you're basically always going to be same, square matrix. But you had to see the non-square to see where things go and to see, oh, yeah, one row space has nothing to do with the other, that kind of thing. Eventually, we're going to concentrate on same to same because that's where all the actual application truly is. But we often start with different, so we can see where things go and the dimension and the shape. Because when I ask you to write the matrix of the transformation, it actually makes it much easier if it's not square. You can't mess it up because you know what the shape is. But if I went 3 to 3 and now I have a 3 by 3 matrix, might I incorrectly write the transpose? I mean, that is the kind of mistake we could make early on because I don't see the difference. That's why I always start with this type of example, eventually working towards the square one. Okay, Rampton, you had a question?
So if you can go back and forth, does that mean that any verse has to exist?
A little ahead of yourself. Yeah, that's a week from Wednesday. Yeah, you're jumping into the future, and that's actually huge. If you didn't hear what he said, going back to baby algebra, everything in mathematics, everything has an inverse. What's the inverse of y equal x squared? You're thinking, it means you're doing it wrong. X equal?
Square root x, square root y.
Plus or minus?
Y equal x squared, the inverse is x equal? Y equal x squared, the inverse is x equal y squared. That's it. There is no other trick to perform. Inverse means you change the roles of input and output. So if it's y equal x squared, the inverse is x equal y squared. Now, is x equal y squared a function? No, it's a sideways opening parabola. Oh, so if I tried to solve for y, I'd get plus or minus root x, but that's not the inverse. That's just describing what the graph is. Everything has an inverse. Now, in terms of function world, every function has an inverse, but is every inverse a function? No. When will the inverse be a function? We know this from baby algebra. I know this because I just reviewed this in the 116 class last week.
When it's 1-to-1.
When the original function is 1-to-1, the inverse will also be a function, because if I'm going uphill, then the inverse will look like that. If I'm going downhill, the inverse will look like that. But if I'm doing this, the inverse will look like that, because the inverse is basically the same graph flipped over the line y equal x, because I'm swapping the roles of x and y. That's something from remedial algebra that you may have forgotten. Go, oh, okay, everything has an inverse, not every inverse works. So I can show you a mapping this way, and then I can have an inverse mapping this way. If there's a matrix, then there should be a matrix going the other way, but if I'm not 1-to-1, and if I'm not onto, then I can't guarantee that I'm going to get unique answers going the other way. So what Rampton was asking was, if I'm 1-to-1 and onto, then the matrix of the transformation, it makes sense that I ought to be able to go backwards, and that would, in fact, we're going to prove that later, would be the inverse matrix. And that actually is really, really important. But there's other things involved. What about, I have this one to this one, then I want to do another one, then I want to do another one. Compositions of transformations, which are very much like compositions of functions in baby algebra. So a lot of the rules that we know of function actually apply to this really seamlessly.
Can you, like if it's n equals m, can you just kind of keep going through the
I'm sorry.
transformation?
Say it again. You lost me there.
If you have n equals m, can you just keep doing the same transformation on the output of each last one?
Oh, sure, yeah. There are no rules that say how many times you can or can't. What we're really interested in, though, we want situations where it's always easy to go forward. Finding an image is always easy. Finding a pre-image may not be, because the pre-image may not be unique. That's where it gets kind of interesting. Okay? So some important verbiage today. The kernel of a transformation, the range of the transformation. How about the dimension? We've got to come up with names. The kernel is a vector space, by the way. It's a set of vectors, so it has to have a dimension. Now, we need a cool name for the dimension of our kernel. Well, let's see. What set was equivalent to the kernel? The null space. What do we call the dimension of the null space? Okay, so why don't we use that one for kernel? The dimension of the kernel is called the nullity. Oh, never would have saw that one coming. Now, the range. The range is a vector space. What vector space is the range? Well, it's a subspace of this vector space. It could be the entire vector space. Let's just say Rm, let's say this is R4. So my range is either R4, it's a three-dimensional subspace of R4, a two-dimensional subspace, a one-dimensional subspace, or the most boring example, it's only the zero vector, so it would technically be zero-dimensional, because it's, we're never going to do that one. That's not even interesting. But the range is a subspace of the codomain. What do you think we should call the dimension of that range? Rank. That's actually the formal definition of rank. Now, if there is a matrix of the transformation, then it has something to do with the row and column space of that matrix, by the way. I'll give you a hint again. I'm giving you stuff way ahead of time. The range of the transformation is the column space of the matrix. That's kind of cool. We're going to see that. We know there's a matrix of the transformation now because we saw how easy it is to write it down. That matrix we know has a row space, a null space. It has the row space of its transpose and a null space of its transpose. The two most important parts we're actually going to use, strangely enough, are the null space of the matrix and the row space of the transpose. Because the row space of the transpose, which is also called the column space, turns out to be the range. Whoa. See, we're going to see all these things. And what you're going to see as we go on, the matrices are so important, there's so much information. Oh, by the way, what system of equations produced this matrix? There wasn't one. Systems of equations are way down here. We're way up here. A matrix is so far beyond what we first intended it for, with solving systems of equations using a matrix. I'm doing that next week in my 116. If you want a little review, stop by. I'm going to show them how to use a matrix to solve a system. And they'll think that's the only thing a matrix is used for. Actually, a matrix's That's not plural, that's possessive. A matrix's prime use is for a linear transformation. That's pretty much what, the only thing you're ever going to use it for from now on in math classes is it's going to be the matrix of a transformation. And all of the interesting things from that matrix come from here. There never had to be a system of equations. In fact, there isn't going to be a system of equations unless I'm trying to find the null space. In which case I create a homogeneous system. Isn't that crazy? You didn't see that coming. You're like, wow, I thought we were just solving simple equations. Now, we're way beyond that. And the uses are so far beyond that. That's what's so cool is I'm going to be opening up doors where you're going to see there's so much more you can do. You didn't realize it was there. My favorite statement, you've heard me say this before, you're going to answer questions that you didn't know there was a question. Forget you didn't know there was an answer. You didn't even know the question existed, and you're going to be answering those things. Crazy cool stuff. So let's do a little bit. Let us suppose, hold on. Because we're going to do more of this next day. So let me start with something real simple. T is going to map R3 to R3. T is going to take X1, X2, X3 and produce X1 minus 2X2 plus X3, 2X1 plus X2 minus 2X3, and let's say,
An extra comma in there?
that should not be a comma there. Oh, thank you. And let's say negative x1, negative 3x2 and plus 3x3. Okay? And do a few questions. First question. Find the image of v equals 4, negative 2, 6. Find the pre-image of, let's say, negative 1, 4, negative 5. Okay, and third one, find the kernel of T. Okay? I want to try all three of these. And do them in this order, it'd be easier to answer the question. Oh, you know what? Let's make a fourth question. You could probably do at the beginning. Find A, how's this? The matrix of the transformation. You can do that one at any point because you don't need, well, you kind of need it, I guess. Got an answer to this one?
14 minus 620.
Does anyone agree?
Yeah.
Good. So the answer is unique. The answer to an image should always be unique. Okay, it's just like when you're doing a function in general. This is a form of function. So one input should only produce one output. Now the next one does not have to be unique, does it? Okay, the next one. So now I want to say t of x1, x2, x3 equals -1, 4, -5. Well, here's where I think finding the matrix might be easier. Okay? If I write the matrix, because then I can just continue from that point. So the fourth question was, what's the matrix of the transformation? I think we'll all get that it's 3 by 3. So the easiest way to do this is look at the first term and look at the coefficients. That will become the first row. Okay? So is it 1, 1, -2, 1. And the second one is 2, 1, -2. Then the third one is -1, -3, 3. Now, how do I know this? Because if I go like this, I'm not going to do the whole thing. If I do this, then when I multiply that out, what's the first thing I'm going to get? Is the first term. And then when I multiply that out, the second term, I'm going to get verbatim exactly those terms, aren't I? That's why I know this is the correct matrix, because it will reproduce that vector. So what do we want to do here? We want to make this equal to -1, 4, -5. Now, there's several things we can do correctly. We can do a determinant, we can do an inverse. Row operations is still probably the fastest. Tell me why row operations is usually a better choice at this point. I mentioned this last day, you might have forgotten.
Because if the inverse does not exist, then
Because if the inverse does not exist, then there's not going to be a unique solution. So trying to find it through other means, I may reach a dead end. What if this is a parameterized solution? Well, then the only way I'm going to find it is by doing augmented. So that's why that's probably the safest way to start this problem. -1. So at least I know Ramton was listening. Okay, so let's do this. If I take -2 row 1s and add it to row 2, I'm going to get 0, 5, -4, 6. Add row 1 to row 3. All right, I'll get what? 0, -5, 4, -6. I noticed something here. So if I take row 2 and I add it to row, row 2 added to, sorry, try this one more time. I'm going to get a row of zeros. Now, lately I've noticed sometimes we make a mistake right now. Everything's correct. I have 2 non-zero rows. I know I have to parameterize. But here's the mistake I'm talking about people are making. They see 2 columns with multiple numbers, therefore 2 parameters. Is that correct?
No.
No. If I have 2 parameters, that's what I'm going to end up with. But couldn't I do row operations to put a 0 here? Not that it's convenient, but I could do that. I know how to do that. And the problem is when I see these 2 columns and I'm thinking 2 parameters, that's an error. The rule is always how many variables, how many non-zero rows. The difference, I have 3 variables, I have 2 non-zero rows. That's why there's 1 parameter. Now, all parameterizations are legal, not all parameterizations are efficient. And the nature of this thing, I'm going to have fractions one way or another. There's no way around it, so I just put up with it. So what parameterization would you like to do here? I still like starting with x3, but you could use x2.
X3 equals 5.
5,
5t.
5t, good. then what's x2? Well, obviously it's going to involve 4t somehow or another, but that 6 is there. So I'm going to do the algebra. 5x2 minus 4 times that, that'd be minus 20t equals 6. So 5x2 equals 20t plus 6. So x2 is what?
T plus
Plus 6 over 5. I would prefer to avoid the fractional coefficients of my parameter. The other number being a fraction is unavoidable. It's going to be a fraction no matter what you do, but I can avoid these being fractions. And in the long run, that's really the only part that truly matters. Now, x1 minus 2 times this plus this must equal negative 1. Yeah. So I've got 1 minus 8t minus 12 fifths plus 5t equals negative 1. So that's 1 minus 3t equals negative 1 plus 12 fifths, which equals 7 fifths. Oops, I'm sorry, not 1. Sorry, excellent. Thank you. I saw that too. Our minds are becoming one. That's really scary to see. You're going to start dressing like me after a while. At that point, can't help you. So what do we got? 3t plus 7 fifths, is that correct? I mean, it's not pretty, it's what it is. I don't have any control over that part. So now it appears, this is still all answer to number 2, it appears any vector of the form Now, here's why, one of the reasons we prefer a vector to an ordered triple. Now, when you first started doing this kind of stuff way back then, you wrote the answer as an ordered triple, and that was fine. You thought of it more like a point in space. But there's no algebra to points. A point cannot be manipulated in any way, but vectors can. So I can pull this apart. This is the main reason we learned to do this. So if I did it correctly, that's the answer. Now, the check is real simple, okay? If I didn't lose anything. The check is real simple. Let's take this and let's put it into here. So 7 fifths minus 12 fifths is negative 5 fifths or negative 1. 14 fifths plus 6 fifths, that's 20 fifths or 4. Negative 7 fifths, negative 18 fifths, that's negative 25 fifths. So the particular part definitely satisfies that. What about the other part? What about 3, 4, 5? 3, 4, 5. So 3 minus 8 plus 5, that's 0. 6 plus 4 minus 10, that's 0. Negative 3, negative 12 plus 15, that's 0. That's a good thing, okay? So everything we have is true, everything we have is correct. But probably the most important part of this entire problem is identifying the kernel. The kernel of the transformation is the same as saying the null space of that matrix. And we found the null space of the matrix, didn't we? So what is the kernel of T? It's a vector space, so we want to use the proper notation. How about span of what? That was awful. I can do brackets. There we go. The span of 3, 4, 5. Now there's question 5 and question 6. Is T 1 to 1?
No.
Because
There's a parameter. The kernel is not 0.
the kernel is not only the 0 vector. Is the 0 vector in the kernel?
Yes.
It has to be. Yeah, it would be impossible for it not to be because the span of that means every multiple, so the 0 vector is a multiple of that. Is it 1 to 1? That's a harder question. Is it 1 to 1? I'm sorry, we just did one. Is it onto? You told me it's not 1 to 1 because the kernel is not only the 0 vector. Is it onto? We haven't actually formally done the proof of that, but you know the answer because of why. Why do you know the answer to that? I haven't proved this yet. This is next time. But I was going same to same. So what did I say about going same to same? It is both Or neither. And we already said it's not one-to-one, therefore it cannot be onto. It cannot be onto. I can input anything into this, but will I get back all of our 3, do you think? No. I won't get back all of our 3. I'm going to get back a 2-dimensional subspace of R3. How do you know that? Think row and column space of your matrix. How do you know that?
There's 2 non-zero rows in the matrix.
Okay, we could say the row space of A has 2, so the rank of A is 2. So if I looked at A transpose, its rank would also be 2. That's a great way of looking at it. You could also say the dimension of both the rows and the columns is 3, and my nullity was 1. So my rank has to be 2. What did I say rank was equivalent to? The dimension of the other R word. Range. If the dimension of the range is 2, but the range lives in 3D, then the range can only be a 2-dimensional subspace. All of these things are things we already know from the past. We're just now applying them in a different context. So it's kind of cool. So all the things we learned before we're going to use, but in a different point of view, but all the same language. That's a good thing, by the way, that the language isn't changing.
Yeah. So to be one-to-one, it needs a nullity of 0 and a rank of.
Well, it just needs a nullity of 0.
Yeah.
1-to-1 is independent of the other side. 1-to-1 is only the first step. Now, the fact that these were same, we like that. Because from an actual usable application standpoint, that makes our life better. What we're looking for in the end, we're looking for sets of vectors that do certain things. I'm looking for vectors that produce certain things. And that's too abstract right now, but in a few days, we're only spending 4 days on this chapter. So in a couple days, we'll be able to start seeing outcomes where we're going to be doing things and you're saying, hey, those vectors give us this type of outcome. Every other vector gives us something goofy. There's something special about those vectors that give us this outcome, and we're going to learn how to find those vectors. That becomes the entire point of the course, is finding those vectors. And you guys know what those vectors are called? Eigenvectors. We just don't have any idea what they are yet. Oh, it's so close. It's so close.
Isn't that what you're like researching right now?
That and other things, yeah. Yeah. It's, the applications are so widespread, and I don't mean abstract. I mean really applied. Good, let's go ahead and stop that, because I don't want to